This tutorial illustrates how to study and design transient structural dynamics using dynamics for spaceclaim. We'll be looking at a simple example, an electric motor mounted on a stationary platform. The method presented applies to many applications that include powered sources of mechanical vibrations. For instance, home appliances, power tools, industrial equipment, pumps, turbochargers, turbines, vehicles, vibratory feeders, and just about any system that involves one or more powered source of mechanical vibrations. Let's outline the task. We have a motor that is going from 1 RPM to another. There is a small imbalance in the rotor as permitted by manufacturing tolerances. This causes vibrations before, during, and after the transition. In order to design this mechanical system, we need to assess what is actually going on mechanically. We need to know the displacements, the loads that occur, and find cost-effective ways to reduce them. More specifically, we need to retrieve the load spectrum in order to calculate the durability of the design. Note that this engineering problem can only be solved in the time domain. Modal analysis and other traditional methods are blind to the transient nature of the system. Our model consists of a rotor, stator and casing, supporting frame, and an external load. The rotor is connected to the casing by elastic joints that reflect the mechanical behavior of the bearings. In turn, the casing is mounted on the supporting frame by a set of dampers. If desired, one can capture the dynamic response of the supporting frame and other substructures by implementing the lumped elements method. But in this case and many others, we can assume that the frame is stiff compared to the suspension elements and thus irrelevant to the analysis. Next, we specify a target angular velocity, nominal torque, and back EMF of the electric motor. Note that we have not yet allowed the system to quite settle in. It is sitting on a set of elastic dampers and is effectively floating in mid-air at the precise instant when the simulation starts. Therefore, we should give the motor a few seconds to fall into its stationary resting position before we rev it up to study its dynamic behavior. This is done by using the sequence editor and simply postponing the activation of the motor torque until the motor is at rest. We now have a powerful model that gives us access to a wealth of useful information and means to investigate and improve the design to our heart's content. It takes less than 20 minutes to do this complete setup, including the plots in Dynamics for Spaceclaim. We can rapidly compare a selection of different dampers to see how their individual properties affect the rotor's displacement and the load spectrum. These simulations run at approximately real-time speed on an ordinary PC. As you can see, the choice of dampers has a tremendous impact on the dynamic behavior of the system. We can also experiment with the geometrical design and quickly find ways to improve the system even further. With all this data available, you can now extend your engineering analysis by exporting the produced datasets to take full advantage of the FEA and rainflow counting tools of your choice. To recap, this video illustrates how to analyze the transient dynamic behavior of rotating equipment using Dynamics for Spaceclaim by Algoryx. Traditional methods are simplified abstractions of the system and cannot determine vital data, such as the loading histories and displacements during transient events. simulation stability, speed, true-to-CAD dynamic contacts, user-friendliness, flexible joints, interactivity, and post-processing make Dynamics for Spaceclaim an essential tool when engineering dynamic mechanical systems. I hope you enjoyed this presentation. Thanks for watching.